All right, welcome everybody to week 2, day 2. We are currently studying why optimizers are a good idea. So one of the test cases is a large one. I don't remember exactly how big it is. Maybe a couple 100,000. Thanks for the Josephus problem. What we see here is that with the optimizer turned on, I compiled it with -03. If we run the program, time is a thing that tells you how long a program takes to run. So you say time and you run a program, and it'll tell you how long it ran. We're going to run a.out, redirecting in input file 10, which has, again, I don't remember how many thousands, hundreds of thousands of inputs in it, redirecting the output to dev null. This redirects the input. That means that it comes from a file rather than the keyboard. So when you read from CN, rather than CN coming from the keyboard, CN reads from this file instead. This is how my input tester works. It essentially takes over your keyboard and feeds the input from this file into your program rather than the user actually having to type something in. It's very, very useful for automation and scripting stuff. Unix shell scripting is really, really nice and useful. I don't care about the output of the program, because I know that it's correct. He passed the test case. So this says rather than cout appearing on the screen, send cout into nowhere. Send it into dev null. Dev null is a special file that everything you write to it is silently discarded. So all of the output of the program is being discarded into dev null. With the optimizer turned on, his code took 1.5 seconds to run. So he qualifies for the extra credit. With the optimizer turned off, it's been running this whole time that I've been talking. And it's still running. So the trick, Kearney, was simply to turn on the optimizer. Yep. What's this background? Yeah. Let's open up a new window, I guess. So the way that you compile things with an optimizer is, so for one thing, we have an alias set up for G++. And it turns on debugging by default. It turns on the base optimizer. And actually, yours is probably different. So let's go into Vargas's account. And if we look at the alias that we have set up for G++, you'll see that the address sanitizer is turned on. And ubisan, the undefined behavior sanitizer, is turned on. This is great for doing development work. It also uses the debug standard library. Slow, slow, slow. I'm not talking about San Luis Obispo. I'm saying it's slow. Address sanitizer slows you down by somewhere between 2 times and 10 times. And the debug glibc adds insanity checks for every access you do. All of these things are going to slow you down by an order of magnitude. So, as you can see over here, it's still running. Okay? Now, and you do not have, you have debugging turned on, and all the other stuff is just for like warnings and things like that. So you don't have the optimizer turned on at all. Okay. So if you have an alias set up, how do you run something without an alias? We'll do a little bit of a Unix lesson here. You compile it like this. / means don't use the alias. So if here I am as Vargas. Let's see if anybody else is running things on the server. Nope, Guerrero has been running for 4.5 minutes now. Oh, did it finish? Nope, still going. Okay. So if we compile Vargas's code manually, compiles is fine. We have an executable that's 700K in size, and if we run it, it'll, who knows, maybe be as slow as Guerrero's. Now, if we want to compile it without the aliases, with all the safety stuff turned on, /G++ -03. 03 turns on the highest level of the optimizer. Sometimes you'll see an 04. I guess that's for like experimental stuff sometimes. But 03 is the highest level of optimization. Main.cc, like that. The / says turn off all this alias stuff, just run base G++ as if it was not aliased. Turn on the optimizer, compile it, and then if we select the over here, we can see that Vargas's actually runs in 1.2 seconds. So his code is actually faster than mine. So congratulations, Vargas. You win a prize. I thought you meant by optimizing the code the entire time. Oh, you should optimize your code, for sure. You should optimize your code. Nothing will save you if you use the wrong data structure. For example, if you were to use a vector for this assignment, which I know some of you did, and you used arrays with a vector, erase with a vector is an order n operation. Erase with a list is an order 1 operation. And since there's n nights, if you use a vector, you will have an order n squared algorithm. If you use a list, you'll have an order n algorithm. It's a very, very big difference in runtime. That's why data structures is so important. Is that you need to pick the right data structure for the job. And this assignment is one of those rare cases where the linked list class is actually useful. Now, if you look online for like Josephus solutions, they usually just print out who survives, but we can't do that here because we need to figure out which order the knights are going to be eliminated in, right? And so I did that deliberately. Because I'm super big, not a fan of students just being able to go online and be like, bloop, bloop, and, just copy pasting code and stuff like that. And the reason why all the solutions online just give you the final person, because you can actually compute that using the power of modulus, using a dynamic programming solution easily, right? If you know who's going to win with 8 people, then you can know who's going to win with 16 people, because 16 people you're just going to eliminate every other person, and then it's going to reduce down to the 8-person case. And if you can solve it for the 16-person case, you can solve it for the 32-person case, because every other person is going to die, and then it will become the 16-person case. And so you can actually generate a solution pretty darn quickly using dynamic programming, but that doesn't tell you the order that they're murdered in or eliminated in. Depends which version of the story you're using. Like I said, it finished. Cool. All right, so let's look at the difference in runtime here. So optimizer turned on, all the safety stuff turned off, 1.5 seconds. Optimizer turned off, all the safety stuff turned on, 436 seconds. So that is a rather large difference in runtime. The last time I've done an assignment like this, I've never done the Josephus assignment before, by the way, but we did something similar. I always mix it up every semester. So we're talking about a 300 times difference in runtime. That's actually bigger than I've ever seen before. Normally you're looking at more of an order of magnitude in difference in runtime. That was 2 orders of magnitude, 300 times difference. Is it okay if we compile with G++-O every time? Yeah, sure, go for it. Compiling with the optimizer will slow down compile times a little bit. For small programs like what we're doing, which is like 30 lines of code, you're not going to notice any difference. So if you want to edit your alias, by the way, when I compile your code and run it on the autograder, it compiles it with the optimizer turned on. That's why Vargas and Guerrero both passed test case 10 and got 11 points on it. Okay. So probably after you know your program is finished, though, yeah, when you're doing development, you really need to have all the safety features turned on, because a lot of you were dereferencing the end of the list, going off the end of the list. You can't do development until you're confident everything's correct, then turn off the safety features. and turn on the optimizer. I use, like I said, I use, this is my default go-to. So I use -01 on by default. So that's, just a very mild version of optimization. It doesn't change the correctness of the code at all. That's my go-to. The autograder, I think, compiles you with vim collect homework -03 -01. Yeah. So could probably try this with -03. Try auto grading it again. See if anybody else passes it with a higher level. Collect homework, Seesaw 26, Josephus. Okay. What makes the different O's different? That's a good question. There's 3 levels of optimization, O1, O2, and O3. There is a massive amount of work that goes into compilers and optimizers. Probably, it's hard to even overstate how important the optimizer is these days. Optimizers these days are probably better than you at optimizing your code in a lot of cases. It's not going to help if you pick the wrong data structure, right? Like if you pick a vector and you're calling arrays on a vector, arrays is an order in operation. The optimizer can't save you from the bad choice of data structure, okay? But if you do something like my line rasterizer is .cc to line intercept, no line. We made an anti-alias line rasterizer in the IS50B. Let's say we're here, and we do int x equals 0, cn, I don't know, cn into x. A lot of people will be like, why are you initializing x to 0? You're just wasting it. The optimizer will know, it's like, all right, yeah, that value is not being used, right? And it'll throw it away. The optimizer will look at, and there's different levels of optimization, right? There's 1, 2, and 3, which is what you're asking about. But there are so many different, very clever things that you can do with code. And if you're a beginning programmer, it's usually actually better to just trust the optimizer to find out if there's useless bits of your code and to eliminate them, right? So if we do x equals 0, x equals 5, x equals 10, the optimizer can easily figure out these instructions here are worthless and will discard them. That's a very trivial, easy thing to do. There's some really non-trivial things that blew my mind when I first saw them, though. Yeah, I'm compiling and running all of your code right now with O3 turned on. Still, it's just Vargas and Guerrero that passed. Okay. So let's say that you wanted to do this. For int I equals 0, I is less than 100, I plus plus, x plus equals I. So x is going to be equal to 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way up to, let's do this, 1 to 100. So we're going to add up all the numbers from 1 to 100, and then we'll output the result. By the way, if we don't output the result, the optimizer will find out we're not doing anything with x and delete it, because there's no point if you have it on the higher optimization settings. Yeah. So Fitty fitty. So what's interesting in O1 and O2 and O3? So at a very high level, O1 is very safe. It does very mild optimizations. And usually that's actually enough to get rid of a lot of the wasteful stuff. Without optimizations turned on, the compilers generate really, really bad code. You'll see the compiler generate code that'll be like store X in a memory and then load X from memory. Every time it reads and writes to X. It writes it to RAM and then reads it right back from RAM. Absolutely no point to that. That read and the write and the read is irrelevant. And so with even the lowest level of optimization, it finds all of those really basic inefficiencies and deletes them. That's why I use -O1 by default. -O2 and then -O3 can do progressively more destructive stuff to your code. So it can do things like eliminate functions. Like if you're calling a function and the compiler decides that the function overhead is not worth the cost, it'll actually just have your code not call the function. It'll do automatic inlining instead. So for example, if right? So if we, instead of doing I++, I'm just making a contrived example here, but there's a lot of non-trivial, non-contrived examples of this. The compiler can figure out that calling this function, and there's an overhead to calling a function. You have to jump to a different location in memory, you have to push the parameters into it, you have to get the values back out of it. There's actually a substantial overhead to a function call. And the compiler's like, all you're doing is adding 1 at the end of the day. And so it will eliminate the function call entirely. And so higher levels of optimization, it won't even follow the commands that you tell it to follow, right? Because it knows better than you. It's like, that's irrelevant. We don't need to call a function. We just put a 1 there, you know? So the optimizer will at higher levels of optimization. I don't remember when automatic inlining is. Might be O2, might be O3. It'll just eliminate that function call entirely because it's pointless. So it's a good question, Krente, and it's a very complicated answer. If you are curious about it, so -O1 optimize turns on these optimize features. So each one of these things can be turned on and off automatically. So these are all different optimizations that some very clever person. I used to have friends that worked on compilers, and working on the optimizer was one of the most productive things they can do because it's just free performance, right? Like if you can discover something new that people haven't figured out before that would optimize the code, you build it into the compiler. Now you've sped up everyone's code around the entire globe, and you only need to figure out how to optimize it once per compiler, right? Whereas back in the bad old days, if your code was slow, you'd have to rewrite it yourself, you know, and like people would be like, oh well, you know, that assignment to 0 there isn't necessary, so we're going to get rid of that and save ourselves a cycle. Or if you're doing like 1,000,000 of these, that's 100,000, that's 1,000,000. Okay. Let's make this a unsigned long. We overflowed before. And you're like, huh, that just did 1,000,000 additions pretty quickly, didn't it? Let's do 10,000,000 additions. So before we recompile, time a.out took 0 seconds. So let's recompile it. And let's make sure we're compiling it with -3. And let's rerun it. 0 seconds. It did 10 million additions in 0 seconds. That's nice. Let's do 100 million additions in 0 seconds. 0 seconds. All right. How the hell is it doing arithmetic so fast? And by the way, this is an actual true story. I was trying to benchmark my CPU here. I'm like, all right, I'll just do a bunch of additions and see how fast it takes to do an addition, right? So now we're going to do, I've lost track here. It's 1 billion. Yeah, let's do 1 billion additions. Okay? 0 seconds. Now let's compile it again with the optimizer turned off. 3 seconds. So, what the hell is happening here? The optimizer look like I said, there are some optimizations that are not immediately obvious what's happening here. The optimizer looked at this and said, you're doing a mathematical sequence. You're adding a series of numbers, and it knows it's up one at a time because it has already replaced this called a foo with 1, and so that function call's already been eliminated. Then it says, okay, you're adding up the numbers from 1 to 1 billion. I recognize that. There is a mathematical formula, n times n plus 1 quantity divided by 2, that will compute the value for you. In fact, if we were to compile this and look at the source code in assembly for it, with the optimizer turned off, the assembly is 316 lines of code, and here's main, and compare, move, call, move, return, move, jump. Yeah, so it's doing a loop, it's doing a call to foo's gonna be in here somewhere. There you go, foo, that's at that place. Okay. So here's the call to foo. So you can see foo is I don't know, 3, 6, 9, 12 lines of code, something like that. In assembly. This is assembly, by the way. Don't worry about assembly. You can just count them and kind of see like how long something's going to take, right? It's not exactly accurate, but you know, you can kind of eyeball it, right? And so you can see that the call to foo is like 12-ish lines of code, something like that, and then it returns. Okay. And then down here somewhere, it's gonna call it, and there's gonna be jump. Okay, and so this code here is the loop, so it's doing a for loop. So it's 1 billion times it's gonna add the numbers together. Okay. Now let's look at this. Now let's look at this if we turn the optimizer on. So we had what before? 300 lines of code, 316 lines of assembly. Okay. Now let's look at it with the optimizer turned on. 192 lines of assembly. Foo. Foo just returns 1. Okay. And there's no call to it anywhere within the code. Nobody is calling foo in this code anymore. All right. Because it knows it doesn't need to. It's inlined it out. And let's see if we can find the actual code in here. Actually, let me show you a better way of figuring this out. This is interesting for you guys. It's actually really important to understand how optimizers work, because you can see what a really big difference it makes. So O1 does these optimizations. O2 adds these in. Add 3 adds these in. Okay. And then there's other options as well. This tries to minimize the size of the executable. If you're going to be debugging, you can't eliminate function calls and things like that because you're trying to step through your program and just things don't exist anymore. Things get moved around, and so if you compile with this on, then it doesn't destroy your code under the scenes. Okay, so there's a website called Godbolt that maybe some of you have heard of. Is there a class to learn this, or just go solo? CSI 45 is where we really talk about this kind of stuff. But it's kind of important. Did you see the 300 times difference in speed? It's kind of important. So here is the program, and if we look at, so this is a website called Godbolt, by the way, or Compiler Explorer. Let's do this in ARM because I read ARM assembly a lot better. Down to ARM. Executor. No, we don't want an executor. We want there we go. That's the assembly. Okay, so this is the assembly. Optimization level. Let's turn on the optimizer. Okay, it's 01. Okay, so with the optimizer off, it looks like this. With base level of optimization, we get this. And yeah, even with 01, look at that. That's the code right there. Do you see that? That's the code. The rest of it is like cout and printing the stuff and then, returning from main, stuff like that. That's your program. Because the compiler figures out that entire for loop can be collapsed into just putting, 50500 into the output stream. That's it. That's how good the optimizer is. And it was really annoying for me because I was trying to benchmark like the arithmetic. I was like, all right, I want to figure out how many multiplies or whatever I can do a second. And the damn optimizer just kept eliminating all my loops. I had to eventually just fill it with random data and then add up random data because if I all these different patterns, like all right, add up 500 twos or whatever, it would figure it out. It would figure out what the answer is. The compiler would do the math and it'd be like, no. And then it'll just do this if you turn the optimizer on. It was really annoying. Is 45 going to be in person next semester? Hopefully. I hope so. This class might go back in person if the coronavirus dies down, which it's not doing right now. So, yeah, we'll see. We'll see how that goes. We learn ARM assembly. ARM 32-bit, ARM 62, ARM 32. Yeah, it's a 64-bit, so it has to do two of them because it's a 32-bit system. So it moves the lower 16 and the upper 16. Okay. Yeah. So it basically is doing the same thing. It can't do 64-bit natively, so it's actually doing. It has to do two to move a 64-bit number. Essentially, it's doing the same thing. It's just pre-computing the answer. And if we up the optimization level, I don't know if anything's going to change. Yeah, maybe. Okay, let's look at this. So, branch of link to that. Yeah, but it's still pre-computing the answer. So, after I gave this spiel during one of the benchmarking assignments, students like, I'm going to get -03 tattooed on my shoulder. So, Yeah, 300 times difference in speed on this assignment. All right, so how do we do the Josephus problem? All right. So let's take a look at how Vargas did it, I guess. Josephus. That's easy. All right, so he's got a function called Josephus. That's what I gave you, I think. He is doing a list. He's pushbacking all the numbers in the list. Creates a pointer to the beginning, and start is equal to start modulus by size. Good. If you don't do that, then it will slow down your code beyond recognition, right? And then he is going to iterate one at a time. You don't actually have to do this. You could actually use advanced for this one. So you could say for this one, you could actually just say advance list by start, and that will advance the iterator that many through the list. The reason why we don't need to go to this effort here is because you've done the modulus, and so if you've done the modulus, it can't run off the end of the list, right? Like if there's 8 nights and you start at night 8, 8 modulus 8 is 0. So you can just use the advance standard library thing to advance however many down the list. You don't have to go to this effort here. Okay. Eliminated night. Erase, and iterator equals list begin. Okay. Interesting. Okay. Yeah, you took a different approach than I did from it. That's fine. Okay. Let's see if your running time is actually affected by it. So it's going to print out eliminated night 5 or whatever. He erases it, and then rather than picking up the return iterator, you should be doing this, right? Whenever you do an erase, it returns the pointer to the next element in the list. That's the proper way of calling erase on a list. But I'm going to assume that Vargas didn't figure that out, so he just started back from the beginning every time. So iterator equals list.erase iterator is the right way of doing it. He is instead going to start over from the beginning every time. Which apparently is fast enough, so, can't complain. So while the list size is greater than 0, if the list size is 1, quit, and return the winner, I don't think this can happen here. But okay, whatever. So otherwise, yeah, so what he's doing here is he's advancing through the list every time. And so that is going to be this is an extra order n operation that you don't need to do. Well, this is extra work that you don't need to do every time. So if you're in a situation with a really long list and a skip of 0, your algorithm is going to be order n squared when it should be order n. So the big O is kind of blown up by this a little bit, by this bit here. But for the big one, I think that the thing is skipping around so much that it doesn't matter. Start equals start plus skip modulus size. So that is the next person to be killed. That's the heart of the assignment here. Power modulus, and then we will advance through the list one at a time. If we ever hit the end of the list, go back to the beginning of the list. And this is the other core thing that a lot of students didn't do. When you hit the very last element in the list, that's not actually the end. If you have 5 nights, the 5th night is not the end of the list. You advance beyond it. Beyond it is the end of the list. If you remember that from CSI 41. That's why I made CSI 41 a requirement for this class. The first element in the list is begin. The last element of the list is not end. First element of the list is begin. This is pointing at the first element of the list. This is pointing at one past the end of the list. So if we have run off the end of the list, then we set the pointer to point to the beginning of the list. That makes it circular. Okay. Then you print out eliminated, you erase it, and he's starting over from the beginning again. So in some circumstances, this code here is going to be order n squared. If skip is 0, essentially. And start, if start is large and skip is 0, then it's going to be an order n squared algorithm. But he came in under the time limit, so it's all good. That's your homework. Okay, so that was your first homework assignment, and that should give you an idea for the kinds of stuff we'll be doing this class. It's going to be a lot of stuff that kind of melts your brain mathematically. The programming, you really do need to know CSI 41 stuff. If you don't know the CSI 41 stuff, I personally had to look up a lot of the stuff using lists because I just don't code using lists very often. There's just not very many, things, relatively speaking, that use lists or need to use lists versus vectors or hash tables. This was one of them. So this was actually an assignment really well suited for lists. So, wish I had a good CSI 41 professor. Yeah, but ask. Just ask, and I'll go over any relevant bits, like I talked about the list stuff. On last Thursday, I think. Yeah. But yeah, we'll continue our exploration of like big O and like what that means and stuff like that. All right, so that was Josephus. Your next homework assignment is going to be implementing RSA. So we haven't gone over the theory of RSA yet. Let me just make sure these libraries are still installed because I reformatted the server, remove a.out, make, okay. Look at that compile time, by the way. Some good compile time right there. Time g++ main.cc. Yeah, we're using the Boost libraries for this one. We're using something called Boost Multiprecision. Read optional, not declared in the scope. Standard equals C++ 20. Why not? So we're using a library called Boost. Boost is like the minor leagues for the standard library. They have something called Boost Multiprecision, so it took 5 seconds to compile. And that's because I included the Boost libraries. Boost drastically will slow down your compile time. It's kind of annoying. Now if we compile this again with the optimizer turned on, let's see if that makes any difference to our compile times. So we'll compile it with the O3 turned on and see if that speeds up or slows down the compilation. I actually don't know, I'm curious. So it took an extra 2 seconds to compile. So with -O3 turned on, do you guys see the difference in compile time? It went from 5.2 seconds to 7 seconds. Let's try it with O1. Let's see how that goes. So the higher levels of optimization settings can slow down your compile time. Yeah, so with O1 it went from 5.2 to 5.7. Right? And just for sake of completeness, let's compile it with -O2. And 7 seconds as well. Okay. Yeah. Okay, so we are going to be using something called the Boost Multiprecision library. Let's turn this back up to O3, which gives us what most people refer to as Bigints. Okay. So before we learn the RSA algorithm itself, let's just look at Bigint. So Boost Multiprecision is a C++ wrapper around GMP. I've talked about GMP a little bit, the GNU Multiprecision library. Boost Multiprecision is just kind of a C++ wrapper around it. And what that is the ability to have ints that don't have a limit, right? Your normal integer ranges from what to what? Anyone remember? Corrente remembers. I'm talking about it in CSI 40 right now. Your normal integer, normal 32-bit integer, what's the biggest it could be? At least 5. Anyone remember? What's the biggest 32-bit integer? Benninghoven Googled it real fast. Yeah. Yeah. If you have a signed integer, the biggest it could be is about 2.1 billion, and if you're doing an unsigned, it's 4.2 billion. This number here is much bigger than 2 or 4 billion. Okay. So let's do this. Copy main.cc up into my home directory, then main.cc. I'll just do a little demo for you. Okay, so this is how you can make a big int. A big int is an integer with no limit. And notice you can't even initialize it with an int because this is way bigger. So you use a string to initialize it. So you pass in a number like that, and then I think you just see it out. ++ main.cc. Look at that compile time. Look at that compile time. It's amazing. Woo! All right. Something exploded. Is it the format library? It looks like it. That's probably causing it, that's my guess. Does CPP have an infinite value? Yeah, it's called the error messages. The error messages are the closest thing you'll see to infinity in C++. Undefined reference to something, yeah, the FMT library. I could probably fix that, but I don't think it matters right now. Okay, so yeah, if we do that, when we run it, then we've got this. We have a variable named x that's initialized to some gargantuan number. We can make another number called y. It's just, I don't know, one more than that. Okay. So let's output x plus y. All right, so big old numbers. You guys see that? Big old numbers. X plus y. So I'll need to turn off the FMT thing or fix it. One or the other. I think I know how to fix it. So we've run it. We get, instead of 1, 2, 3, 4, 5, we get 2, 2, 3, 4, 5. Yep. Do you guys understand? Big numbers. Big numbers go burr. In lieu of the biggest number they have called math.huge. It's funny. Does CPP have an infinite value? Not for integers. For floating point numbers, yes. Floating point numbers, there is NaN, N-A-N, which is not a number. That's what it stands for. NaN is not a number. And if you do like a 5 divided by 0, then you get NaN. And there's also a negative NaN if you get negative infinity, essentially. Because infinity is not a number, so they call it NaN. And so students have made back-end NaN you know, memes, things like that. Do you guys understand this stuff? So you can make a big old number and add them, subtract them, multiply them. Get a really big number. Two big numbers times each other is an even bigger number, right? This would overflow any regular integer by, you know, many orders of magnitude, right? This is way bigger than 2 billion. Big numbers needed in cryptography, yeah, because what is the length of a key when you do RSA encryption? Anyone know how big these keys are? That's the key. And that's not base 10. This is base bigger. Okay. So this is a gargantuan number. Okay. 256-bit is for amateurs. I think 1024 is kind of standard these days. How big an RSA key do I need? Okay, sorry, 1024 is not big enough. 2048 or 4096 bits. Okay. Bit length of primes is recommended to be between 1,000 and 5,000 bits. The largest known factored RSA number is 768 bits long. So 1024 may not be safe. The US says that 2048 is safe to use until 2030. France says they have confidence in it until last year. Yeah. So, yeah. So between 1,000 and 5,000. Something like that. A 5,000-bit number. It's a big number. It's bigger than 32 bits. A 5,000-bit number is bigger than 64 bits. It's quite a bit bigger. Remember, every bit you add to it doubles the maximum size of the number, right? That's a lot of doublings. That's a lot of progressive doublings. A 64-bit number is already pretty big for normal human use. But when we're doing cryptography, these numbers are unbelievably, colossally big. And the, well, I guess we can start talking about RSA at this point. But this is kind of what you need to understand for the next homework assignment. Okay, do you guys get it? There is a class called CPP integer. I don't know why they called it a C++ integer. It doesn't have anything to do with C++. Maybe it's because the MPZ, the multi-precision integer, they just changed the prefix on it from MPZ to CPP because it's a CPP class. I don't know. It's kind of a dumb name in my opinion. It should just be called Bigint, in my opinion. But whatever. So if you make a variable of type CPP underscore integer, that's a variable named X. You can initialize it with a big old number, or you can, if you use the read library, which I recommend here, then you can enter it from the keyboard. And so for your homework assignment, you are going to be doing RSA encryption and RSA decryption using this Bigint library. And we'll go through the math and the theory in just a second. All right. Would this work with Caesar encryption? You don't need to use Bigints for Caesar encryption. You can implement Caesar encryption using an array with 26 values in it. Pretty small. Okay. So it's already 11 o'clock, so let's go ahead and take a 10-minute break. And then when we come back, we're going to run through the theory of RSA. Okay, and then I'm going to, in the break, I'm going to either get the FMT library to work or erase it, one or the other. All right, I'll see you guys back here at 11:05, and we're going to learn how RSA works. It's not that bad. It's not that bad. Peace. And we are back. I've been trying to figure out this linking error. I actually have the answer to it somewhere. This is really frustrating. But as it is, I just commented out the stuff that refers to format, which has been standardized. This is actually a new thing in C++ 20. There is the format.h header, and it's a new way of outputting things in the standard library, which is one of the reasons why I had some hope that my read library, which is a new way of reading things, would be standardized, but there doesn't seem to be too much excitement for that, so who knows. Yeah, you can call std : format, and then whatever you put within, whenever you put a open-close curly brace here, it'll substitute in the arguments, and you can actually put a number in there and say argument 1, argument 2 if you want them in a different order. It's pretty cool. Let me just see actually if this works on the server. G++, main.cc, no such file or directory. So yeah, it looks like format, which is supposed to be part of C++ 20. Let me just verify this. std C++ 2a. Can't find it, so it's not yet out. So even though C++ 20 came out last year, it's still not on the server yet. So can't use it yet. So format, which is now standardized, was based on FMT lib C++, which is not exactly the same thing, but more or less the same thing. And it allows you to basically do printf style printing, and you can substitute things in here. The trouble is, like, when I'm trying to format print one of the CPP ints, it explodes. It gives like page after page of error. And I know I have found the answer to it before, and I was going through my history trying to find where the answer was, because I've found the answer to it, and it's just frustrating not remembering what the answer is. So rather than worry about that, I just pulled it out because you don't need it. You can just see out things. So let's learn RSA encryption. So we talked last time about the world of espionage and stuff like that, which is kind of fun. So today we're going to learn about RSA encryption. Okay, so RSA encryption is that public key encryption that we talked about. Basically, you start off by generating large primes. Okay, you randomly generate a large prime. Now, here, okay, before I get into it, let me tell you what the core observation that Rivest, Shamir, and Adelman came up with when they developed RSA encryption. They were trying to come up with something called a one-way function. Okay? They wanted to create a one-way function. A one-way function is something that is easy to do one way and really hard to do the other way. And in math, you know, it's kind of like, well, you know, most things in math are reversible, right? So if you have, for example, I don't know, 2 plus 3, you can subtract 3 and get 2. Most things in math are symmetrical, and so it's just as easy to go one way as it is to go the other way. And so they were searching for a one-way function specifically to make this kind of public key encryption, because with public key encryption, it's very, very easy to encode something and send it to Glenn Greenwald at The Intercept, or formerly of The Intercept. It's very easy to encode an email and send it to him. It's very hard to decode. Okay, it's a mathematical transformation that is easy to do one way and very difficult to do the other way. It's sometimes called a trapdoor function because it's very easy to fall down a trapdoor. It's very hard to get back up out of it. Okay, And so their core observation, I think they were actually kind of drunk at the time, if I remember how the story goes. They'd been drinking, and then they realized that it's a lot easier to make to multiply two numbers together than it is to factor them back out, right? So if you take 5 times 4 and get 20, it's a lot easier to do the multiplication than it is to factor 20 and get 5 times 4. But 5 times 4 is ambiguous because they're not prime. So assuming you have prime numbers, 3 times 7 is 21. Going backwards from 21 to 3 times 7 is actually a lot harder. And we don't realize this because whenever we learn factoring as like a kid, we have small numbers, and factoring small numbers is easy, right? Because if they're on the times table, we just can immediately do it in our head, right? 14 is 2 times 7, right? Like, it's not a big deal. But as it turns out, factoring things is actually really, really hard. I wrote the code to do factoring the other day, where we're trying all these numbers from 1 up to square root of n. And you just, well, not 1, 2 up to the square root of n, trying all these different numbers. And so if you have a number that is 500 digits long, you're not going to be able to iterate through even a small fraction of all the possible numbers to factor. So multiplying two numbers, easy. If you get two prime numbers and multiply them together, then you can do that very quickly. Going the other way is very hard. Okay, that's the core observation for. We all love the read library. Don't feel bad. Thanks. That's the core observation for RSA. Okay. Now there's a couple hard things in there. First of all, how do you randomly generate a prime number that's huge without factoring it? Right? Because remember, factoring things that are long, let's just say, is impossible. Okay? So if you have a really big number, you can't factor it for all intents and purposes. If you have a quantum machine, sure, maybe. Shor's algorithm can do it pretty quickly on a quantum machine, but quantum machines are still kind of in their infancy right now. So how do you make a prime without factoring it? Anyone remember? Anyone remember Fermat's little theorem? If a number is prime, whenever you do the x to the y minus 1 mod y, if y is prime, you remember that? How do you generate a large prime? Well, you guess a number, an odd number. Even numbers aren't going to be prime, right? Except 2. So you guess a large number. Like, I'm just going to guess 371377. Okay? I don't know if that's prime or not. I just randomly made up some numbers. And I'll just randomly guess a number, and I'll see if it's prime. And I'm going to see if it's prime by doing the Fermat's little theorem. There's actually a faster test called Miller-Rabin, but whatever. We know Fermat's little theorem, so we'll just stick to that. So this is y. Okay? And if you remember Fermat's little theorem, x to the y minus 1th power modulus y is going to be equal to 1 for all x, other than 0. 1's probably not very useful either. Right? So you pick a number from 2 to, y minus 1, right? For x, you randomly pick a number, and you do the POW-M. This is POW-M, right? This is POW-M. You're doing exponent and modulus. If you get 1, it might be prime. If you get 2 or 3 or something like that, it is not prime. 100% not prime. And then you pick a different number. And then you just keep randomly guessing numbers until you get a prime. Okay. If you do get a 1, then it may be prime. May be prime. And so you do it again. You pick a different x, you pick a different x, you pick a different x, you pick a different x. Until you've done enough times that you keep getting 1 and you're happy. So you might do it 20 times, 30 times, 50 times, up to you. And you might be wondering, like, how many random numbers do you have to pick from until you get a prime? It seems like, when you're talking about a 1,000-digit long number, or 1,000-bit long number rather, which is much smaller than 1,000 digits, you would have to like guess numbers forever, right? What is the theorem name? That theorem here is Fermat's little theorem, and we went over the proof last time in class. Because when you're in a prime modular world, anytime you do a multiply, it does a permutation, and so there's a very beautiful proof that you multiply all the numbers together, you collect the product, and you end up with this. If y is prime, then x to the y minus 1 power modulus y is always going to be 1 for x between 2 and y minus 1. It's called Fermat's little theorem. And so what you do is if you want to see if y is prime, you just do this over and over again with different x's. And if all of them turn out to be 1, then congratulations, you're prime. If any of them are not 1, if you get a 2 or a 3 or a 7 or whatever, then it's 100% guaranteed not prime, and you pick a different number for y. And you keep doing this until you get a prime. That's how we generate prime numbers for RSA, except we don't use Fermat's, we use something called Miller-Rabin instead, which is a little bit faster. Okay. It's a weird concept, isn't it? It's like I hold up a card with a big number on it, and a person comes up and just says, "That's a prime," and the next person comes up and says, "That's a prime," and the next person comes up and says, "That's not a prime." You're like, "Oh, it's not a prime." You rip it up and write down another random number, and each person that says that's a prime, it's like a 50-50 if it's actually a prime or not a prime. And so you just get enough random people coming up to you and be like, "Yeah, that's a prime, that's a prime, that's a prime." And if all of them agree, all 20 or 30 agree, then there's a 1 out of, let's see, if 32 people agree, it's 1 out of, 2 billion chance that it's not a prime. It's pretty good. It's pretty good odds that it's a prime. If it really matters to you, you can get more blind witnesses, as they're called. Uncertainty in math scares you. Yeah, but here's the thing. Miller-Rabin is 75% accurate. So you can have certainty out to however many digits of precision you want fairly quickly. If you get 64 of them, like, it's going to be unbelievably unlikely that it's not a prime. So the question is, like, how many candidates do you have to go through? And the really interesting thing is you don't actually run out of primes. Like, I used to, because, if you look at the primes, you start with 2's a prime, 3's a prime, 4's not, 5's a prime, 6 is not, 7's a prime, 8's not, 9's not, 10's not, 11's a prime, 12's not, 13's a prime, 14's not, 15's not, 16's not, 17's a prime, 18's not, 19's a prime, 20's not, 21's not, 22's not, 23 is, 24's not, 25's not, 26's not, 27's not, 28's not, 29 is, right? So primes start getting more and more rare as you go up. But what's really interesting is that the average chance that something is a prime is inversely proportional to the number of digits it has. So if you're generating a 100-digit number, you have about a 1% chance that that number is prime, roughly speaking. It's a little more complicated than that. There's an interesting proof of that. But yeah, if you just make a random 100-digit number, there's just ballpark. There's roughly a 1% figure that any odd number you pick with 100 digits in it is prime. So you don't actually have to try that many. A computer can easily try 100 numbers. You run the Miller-Rabin test on it 30, 50 times. Cool, you got one prime, you do it again, you got another prime. Done. So you start off by randomly generating P, randomly generating Q. Okay, so P and Q are primes. So you make a big old prime here, you make a big old prime here. That's the beginning. Okay. Then you do the following math. Here are the steps for RSA encryption. You compute the product of the two primes, call n. Okay. You compute what's called the totient, Euler's totient. Don't worry about it, it's a totient. It's there's a lot of math theory that goes into Carmichael numbers and all this kind of stuff. It doesn't really matter. What it means for you when you're writing the code, because you're going to have to write this code, is you take p minus 1 and multiply it times q minus 1. That's what you have to... we can get into what it means. It really doesn't matter. You can do this, right? You know, if our primes are 11 and 17, then n is going to be 11 times 17. T is equal to 10 times 16. Do you understand? And you could do this with the CPP integers. Mind your P's and Q's, everybody. Right. So if we're in the RSA assignment, which is what you all will be doing, you need to compute n, right? Using P and Q, compute the RSA numbers, right? So you're going to set n equals to P times Q. N is equal to P times Q, just like that. So once you've generated P, once you've generated Q, you just set n equal to P times Q, okay? And then T would be P quantity P minus 1 times quantity Q minus 1. You guys understand? Like that, this is how easy RSA encryption is going to be for you guys to write. It's actually really not that bad. Okay. Okay, so E is always going to be 65537, as long as N is over 65537. E, this is just a standard number used. It could technically be any prime number. If you're using a smaller n, then E should be a prime number smaller than it. Okay, and so this is your public key. That's it. E and N. In fact, you don't even usually need to publish E because, I mean, I guess you do, but everybody always uses 65537. It's a standard. And so all you really need to do is publish this number here. That's it. That's your public key. And as long as nobody can go back from the public key to the primes, it's secure. Okay, see that? So you randomly generate two gargantuan prime numbers, you multiply them together, multiplying them is easy. It takes a fraction of a second. And then you just publish it. That's it. That's your public key. You just publish the product of two prime numbers. And as long as nobody can go backwards from that gargantuan number to P and Q, and nobody has found a fast factoring, like there's fast algorithms to factor, but they're not fast enough. They're not like fast enough to do it in a reasonable amount of time. You're talking like heat death of the universe kind of long, right? If you make your primes big enough. It's really, really slow to go backwards. So, and if anybody ever does figure out how to go backwards, you just make your primes bigger, right? Because, you know, it'll take a little bit longer one time. Because you only have to do this once. And so if you want, you can make a 1000-bit number if you want. Like 2000s, if they're getting close to breaking 1000, do 2000. 5000. Remember, every bit doubles the amount of work they have to do, right? So just make it, 100,000. You know, like you can make these bigger way faster than people can factor it. Okay. And so that's it. You just publish that online, and then people will email you using your public key. But the only person who can decrypt it is you with your private key. Okay. So how does that work? So you convert the inverse. Do you guys remember the multiplicative inverse? Remember how we were talking about modular division last time? You're asking where it's going to come up. The multiplicative inverse, which is the core part of modular division, you compute the modular inverse of 65537. 65537 again is standard in the industry, and the reason why it's standard is because you technically have to publish it, but if everybody uses the same number, it doesn't reveal any information about you. Right, like if one person's algorithm always used a different prime number, then people would know what algorithm you're using and you'd be leaking information. Also, 65537 has some fairly nice properties, and it is also accelerated, hardware accelerators and things like that. So what you do is you compute the modular inverse of E under the totient, and that is your private key. So you don't even have to write down P and Q. All you have to do is write down D. Okay? And you write down D and you write down N. And this is it. So you publish your public key, you hang on to your private key. Now, how does the actual encryption work? The encryption works like this. They take the message, M is like an email, and you need to convert your email to an int, which we can talk about. But you convert your email to an int. Let's say let's say you're going to send the number 42. Okay, you want to send the message 42 to somebody. You take 42, you raise it to the 655th, 537th power, modulus, whatever 10 times 17 is. Actually, this won't work because E is too big. Let's make bigger primes, I guess. Think like, whatever. Let's use a smaller E then. That'll be simpler. Use like 7. Okay, so 42 to the 7th power modulus N. Oops. N is just 11 times 17, which is 187. 187 on the... It's probably before your time. Okay, so if our secret message is 42, then we raise it to the eth power. In this case, I'll just be using 7 because N is small. Raise it to the 7th power, modulus it by 187. Okay, so we would use the pow_m function for it. That's what we talked about last time. 42 to the 7th power is that. Modulus 187 is 15. And we send over the internet, we send the number 15. Okay. And then on the decryption side, we take the number 15. That's our secret message. That's our encrypted message. We raise it to the dth power. Only we have D, right? Only we have D. This is our private key. Okay. As long as we keep our D safe, then nobody else can decrypt this message. All anybody over the internet sees is somebody sent me an email saying 15. Only I can decrypt it. Okay. So anybody on the internet could send this to me because my public key is published. On my website somewhere, I've got my E and my N published. I've got 187 published on my website. And so what they do is that I have my E and my... I have E as 7, N is 187. So they take whatever secret message they're trying to send, raise it to the eth power, 7, and then modulus it by 187. And they send 15 to me. And then to decrypt it, I raise it to the dth power. D is the modular inverse mod T. Which at this point I'm almost wanting to... see, the totient is 10 times 16 is 160. I probably want to do this on the computer at some point, but I'll just show you the math without actually working it out. So it will be D, whatever number that is, 15 to the dth power, modulus N, modulus 187. And if I did that right, then it will give me 42. Okay, so that's RSA encryption. The proof of this is a little bit hairy. I've run people through it before, but their eyes kind of go cross-eyed a little bit. Like, why does this work? Almost seems like magic until you like dive into it. But this is it. It's one slide. Randomly generate 2 primes, multiply the primes together, that's N. Multiply each of the primes minus 1 times each other, that's T. Always use 65537 for E, assuming your N is big, which it should be. compute the modular inverse, which I have given to you on here. So this is a function that computes the modular inverse. So given t and e, it computes the modular inverse, which is d, which I stole off of Stack Overflow. And yeah, so that'll generate, this will generate your d here. And that's it. So that generates all of the constants. There's only 4 constants that get generated. Oh, I guess 6 counting p and q. So you're going to generate p and q randomly. N is the product of p and q. T is the product of p minus 1 times q minus 1. E is always 65537. And d is the result of this function. You pass in t, you pass in e, it gives you d. That's it. That's your homework assignment. Okay. It's not stealing, it's our code. Yeah. Well, I mean, that's why they put it on Stack Overflow, right? To help people. So, yep. That's it. You'll have a week to do this. Okay, we got 20 minutes left. So let's. Seems pretty straightforward. It really is. It's for something as like fundamental to modern society. It's actually, and it's not really used that much. There's sort of better algorithms now. This was published back in the 70s. There's what's called a discrete elliptic field. Elliptic curve, yeah. So one of my professors was one of the big names in this field. So let's see if we have a picture of it. It doesn't really matter. So there's other algorithms, but RSA will kind of give you a feel for like how cryptography works. It's not bad. Let's see. So there's no, that's not my professor. That's a village in India. Okay, well, it doesn't matter. So, so this, like I said, RSA is it'll give you kind of a good feel for the cryptography field. When I started college, I was really interested in computer security and, hacking and, that kind of stuff. It was maybe the product of watching Hackers the movie on a press junket. No, I'm kidding. It was just an interesting field. And what I realized after taking a couple classes in it was that it was mostly math. Well, it's two things. Like, if you're talking about cryptography and things like that, it's mostly math. It's really a math-heavy field. And then that's paired with social engineering, which is very much not math, but like just working on the human elements, right? And so like you call somebody up over the phone, hey, it's tech support. Hey, can you give me your password? I'm trying to log in as you. Like the social engineering thing is completely separate from the math thing, sort of. And then there's the technical side where like you have to look at a program and see where the vulnerabilities are in it. Like if they have an array and they don't bounds check properly, then you can go beyond the edge of the array and overwrite their program and have it execute random code, things like that. So it was a kind of interesting field. Is that? Have you ever hacked? We only got 20 minutes left, so ask me that another time. So let's talk about other uses for RSA. So the primary use of it is so that you can communicate with somebody over the internet, right? If you have a public key and they have a public key and you both have your private keys, then you transmit to them using their public key and they decrypt it using their private key. And then when they send a response back to you, they encrypt using your public key and they decrypt using their private key. And so you can have a communication securely over the internet with anybody without having ever met them before. As long as the keys remain secure, then you can have a private conversation with anyone over the internet. It's really mind-blowing that we can do that. Because before you had to sort of know each other already to trust them. And with this, all you have to trust is that the key wasn't compromised, right? Like if somebody were able to take out the website where Glenn Greenwald's public key is, they would be able to replace it with a different public key. And if they did that, then you'd be sending encrypted data to not Glenn, but to somebody else, right? So there's a whole another part of all this story involving key management and trust chains and all this kind of stuff. So, got to involve patterns for security and stuff like that. Yeah. A lot of times you'll see common patterns in code that is vulnerable. So this is the primary use of public key encryption, but there's another use. You can actually have it go the other way. You can actually send an email to somebody using your private key. So like, let's say I'm going to send, let's say that one of you wanted to petition to join CSI 26. The counseling office sends me unsecured a Adobe Acrobat document that has the petition on it. And let's say that I want to sign it digitally and send it back to them. It's a weird concept, right? Digital signatures. Like, how do you know that it's me signing it and not Bedencourt? You know what I mean? Like, you know, the counseling office sends this petition form to me, and then Bedencourt can spoof an email from me with a fake signature on it. Like, how do you know? How do you know? Right? It's a weird concept. Because spoofing email is very easy, by the way. You can send email from anybody trivially easy. Email is not a secure system. Hi, this is actually my signature. No fraud here. Yeah, it's like whenever you see those pictures of kids like trying to sign their notes to the parents, you know. Yes, please excuse my son Billy for, you know, and it's super. So, RSA encryption can be used the other way. If you take a document and you encode it using your private key and you mail that out, people can use your public key to decrypt it. Okay? And so usually you don't do the whole file, you do like a chunk of it or whatever. You just have to do enough to verify that that's actually you. Somebody with my private key, which is me. Because remember, in RSA encryption, whoever has the private key is me, right? So if somebody steals my private key, they're me, for all intents and purposes. Maybe even for legal purposes, right? Because it's signed by me. It could carry some legal weight. So it's the same code. It's the same exact math, right? I take the petition form, I encode it using my private key, and then the counseling office decodes it using my public key, because they have access to my public key, right? So if I send you an email that's been encoded with my private key, you can decode it, same math, it's symmetrical. You can decode it using my public key, and that verifies that the person with my private key sent it to you. Doesn't necessarily mean I sent it to you, but somebody with my private key sent it to you, and you can verify that online. And so that's how, like, if you've ever seen like signatures on like Adobe Acrobat documents and things like that, you can digitally, or if you download a PDF off of drivethrurpg.com or something like that, and they digitally sign it, that's what they're talking about. They take their private key and take just a chunk of it. They don't have to do the whole thing, just enough to show that they have the private key, and they encode a chunk of it with their private key, and then you can verify using these trust chain networks of key. There's a whole side of that I don't want to get into, but like you can verify that that is their public key that can decrypt it, so that is them. You know, that has been digitally signed. And Acrobat documents that are digitally signed will have a little thing at the bottom a lot of times saying this has been signed by so and so, and so you can verify it. You can verify the signature. Okay, pretty cool. You guys agree? It's pretty cool? I think it's pretty cool. That without ever having met somebody, you can verify that it's them. At least somebody with a private key, right? Signed it. So, again, there's always the risk that somebody compromises your private key, and then you have to get into things like key invalidation and revoking keys, and like I said, all that key management stuff is another day, another story. All right, so finally, we're going to talk about cryptographic hashes. Okay, so normally we've talked about hash tables before, right? Like if you maybe Bedencourt didn't get into it. Hash tables are my single most favorite data structure because hash tables have order 1 insert, order 1 search, order 1 delete. Okay, so it's pretty good. Constant running time, insert, search, and delete's pretty good. The downside is it loses any ordering. It doesn't remember what order things were put into the hash table. But usually that doesn't matter. Like if you're making a database, it doesn't matter what order people were added to the DMV database. All you care is being able to load customer data fast, right? And the DMV doesn't do this for some reason. I'm not sure why. Like I've told this story before in 41, but like I went to the DMV and they had to look me up based on my name or my address or something, and it took like literally minutes of me standing there. And my computer science brain was going like, why is this so slow? Why? How? What? You know, there's 30 million people in California. You should be able to find me. Are you going through the entire database? Are you going through every person in California doing a string comparison? Because this is appalling to me. You know, if you had properly hashed it, then you'd be able to find it in order 1 time. Okay. So normally when you have a hash table, you have like an array. Let's say you have an array of size 100, and you want to store the value of 420 in it. What you do is you take the value 420, you modulus it by 100, and you write it into array element 20. That's your most basic hash table. Power of modulus. Okay. When we're talking about cryptography, though, we don't want a system like that. What a cryptographic hash is, it's a hash. It's a way of going from all possible documents and emails, which is an unbelievably vast number. All possible files. It's like how many possible files are there on your computer? Yeah, like if you have a terabyte hard drive, it's like 2 to the, you know, it's an unbelievably large number of possible files. And so when you hash it, when you do a cryptographic hash, what you want is to be able to have the same file every time generate the same hash. So if you go onto like PuTTY or something like that, caps lock's on again somehow. I need to just disable my caps lock key, man. So if you go to like downloads for PuTTY, you'll see right here there is a signature. If you click on that, what you're going to see is save that here, and let's open it here. Where'd it go? There. Open it in Vim. Let's see if that's visible. Yeah. So this is a hash. Okay. And what you do is when you download PuTTY, you can run the same hash on it. And if it hashes to the same bucket, so to speak, as this one says it hashes to, it's not really a bucket. You're not even putting it into a hash table. You're just doing the hash operation, right? If it hashes to the same thing that's on the signature, then you have verified that this download here has not been tampered with. Okay? So let's say that I make a copy of PuTTY and I'm hosting it on my server. And you guys can download it from me instead of having to go to the main PuTTY website. All you have to do to check that I haven't screwed with it, because I could put a virus in it and make it so that every time you connect to a server, it emails me your password or private key or whatever. If you want to verify that I haven't screwed with PuTTY, all you have to do is go on to the PuTTY website, download the signature, and then run the same hash function on what you downloaded from me. And if you get the same value as the signature, it's the same file. Okay? So back in the day, we used something called Md5 Hash. and it's not secure at all. But yeah, it was what was used back in the day. So if you were to type in like hello, that generates a Md5 hash of this. Okay. And this is different from the hash tables we learned about in 41, because in 41, you'd probably like add up all the letters and then modulus by the size of the array, and you would get something very predictable. And if we were to like change hello to be like hello, you know, if we went up one number, the bucket that it would hash to would go up by 1 also. But this is not what we want for a cryptographic hash. What we want for a cryptographic hash is for even the smallest change, just changing hello to hello, going up one letter. Look at the hash. Watch how it changes. It's completely different. Do you guys see that? 8B1, A995, 62AC2, DCD. It's completely different. So even the smallest change in a cryptographic hash makes a completely different hash. It's predictable, it's deterministic. If I were to delete this and do it again, I get the same number. But the goal of a cryptographic hash is that I can't, even though this is, you know, much smaller than all possible files, it's still practically, it's supposed to be impossible for somebody to generate a different word that would come up with that same hash there. It's supposed to be. Md5 got broken, and so we don't use it anymore. But it used to be like if you send an email to somebody, you could attach an Md5 hash of your email. Hello, my name is Bill Fermat. I am a prince who recently inherited a large amount of money. Right. So what I could do is, if I send you an email, I could attach the Md5 hash to the bottom of it, or put it in some other place, and that would verify that's a signature. It's a form of signature, right? That's hasn't been tampered with, right? If I had the signature, this is like the putty signature, right? If I had that up somewhere, then you could take this string and Md5 hash it and verify, yep, the hash is the same as the one on his website. Therefore, the email hasn't been tampered with. And this is pretty important. Like, you know, if you send your soldiers a message saying attack at dawn, you want them to be able to verify that you actually said attack at dawn. Okay? So you send that to them, and then somehow they have to have some way of verifying the Md5 hash on the email is the same as the Md5 hash you sent them. And assuming they can do that, then they can look at it and be like, all right, yeah, the message is legitimate. Now, Md5 has been broken. And so Md5 being broken means that I could generate a different string that also hashes to the same thing. And so if I was able to intercept your email, I could switch it out for that other one, and when you Md5 hash it, you get the same string that's on my website saying that's the signature. And that's bad. That's really bad. So if I was able to go like attack at dawn and somehow change it to be like attack at dusk, or like don't attack at dawn, and if I could come up with the same Md5 hash as before, I could switch out the meaning of the email that you're getting. If I could intercept it in flight, I could change it and still have it cryptographically be validated, or not. Yeah, the hash would be the same if I could break it. And Md5 has been broken. So I believe SHA-1 has been, yeah. Md5 is not cryptographically secure. Yeah. She's a genius at breaking these kinds of things. And so in recent news, Apple has a thing. Apple has a thing. Where's the thing? Too many tabs open right now. closed it. It's unfortunate. Yeah, Apple has a thing where they generate a hash of an image to give it a signature, and it's been broken as of yesterday. So you can't trust the signatures on those images anymore. People have figured out a way of coming up with a fake image. So if you have an image and it's signed with like an MD5, or it's not MD5, it's their own thing, it has a signature on it to verify it. People have been able to generate a fake image that will come up with the same signature. And that's bad. It's really, really bad when people can do that quickly and reliably. Because you could always brute force it, right? Try every possible image. Well, that takes forever, right? But if somebody can just generate an image that will hash to the same value, then they can say, no, this was the original image they took. They didn't take a picture of that dog over there. They took a picture of, noise. It's probably what it's going to look like. Let's see here. Yeah, there we go. So they have this dog here, and they have a picture of this. And if you run the hash algorithm on it, you will the neural net hash that Apple's made. You get that hash value for the beagle, and you get that hash for this picture of noise. And so that's bad, right? Because what you can do is you can say, oh, that they posted that signature of that dog. No. Judge, Your Honor, what they actually took a picture of was noise. And I can prove it by showing that the signature matches. Okay. You guys understand? So when you make a cryptographic hash, you want it to basically randomly scatter. Even a small change will cause it to randomly scatter over the entire 512-bit space or whatever. And it should be so unpredictable that nobody could come up with a change like where you could change sell all stocks to buy all stocks and have them hash to the same value. That's the whole point of a cryptographic. What's the dog doing? I don't know. Yeah. So do you guys understand? You want to make it so unpredictable that nobody could do that, where they could just come up with a fake image and have it have the same signature, right? You want to just make them brute force it, like they just have to try every possible image, and that's so hard to do that it's not practical. Yeah. And you can be legally responsible if you've got a signature. If you have your signature on something and they can switch out the email, that's still your signature on it. So, if you buy stocks when you're supposed to sell stocks, or buy Doge when you're supposed to sell Doge, or vice versa, you can be legally responsible for it. Yeah. Right. So, like I said, yeah, a lot of the old ones have been broken. There's a female professor in China that is just a genius at figuring out how to make fake things that will end up with the same signature. This is different from RSA signatures, by the way. This is just a program. You run it on a data set, and you get a signature. You get an Md5 hash, or you get a SHA-1 or SHA whatever hash on it. We use that to verify downloads and to verify emails and things like that. So the RSA algorithm, we're going to be using hash tables in the assignments. No, this is a related topic. This is not RSA. The Md5 and SHA algorithms and things like that are not RSA. Okay. But I can show you how passwords work. So when you store a password on a server, you're not supposed to store the password on a server. Did you guys know that? So, I don't know if I want to show it online. Let me pause the recording. So if we, are we recording in? Yeah. So I just showed the shadow file. The shadow file is where your passwords are actually stored, but they're not actually your passwords. The Etsy password is where passwords used to be stored, but you notice the passwords are not there anymore. They are held as X. Okay. And the actual password is in the shadow directory. And so the shadow file, not a directory, the shadow file has your passwords, except they're not your passwords. They are a hash of your passwords. And so when you log in, what happens is it hashes whatever you type in. Hi, my name is Bob. Hit return. It will hash, hi, my name is Bob, using not Md5, but we'll just use Md5 because it's easy to say. They'll take, hi, my name is Bob, run it through that website that I just had up here. Hi, my name is Bob. Does an Md5 hash. Again, it's on Md5. And it compares this against what's in Etsy Shadow. And if it's the same thing, then congratulations, you've logged in. Nowhere within a Unix system should your plain text password ever be stored. In no secure system should your plain text password ever be stored. I don't know, even though it's my system, I don't know what your password is. Right? And that's good, because if I could know what your password was, if it just stored your password in like a text file, then I would be able to go to, I don't know, Amazon and try your password there, right? If I know that Bigints always uses hi, my name is Bob as his password, I could go onto Amazon.com and type in his email address and type in hi, my name is Bob and just give it a shot, because a lot of people reuse passwords, right? So nowhere within the system should hi, my name is Bob be stored. Instead, they do an Md5, again, it's on Md5 hash. That's stored in the Etsy shadow file. When you log in, it hashes whatever you type in, and it compares them. And if they match, cool. That must be it, because, again, hash collisions are not supposed to be possible. Feasibly possible. Okay. They're possible, but they're not supposed to be feasible. Okay. And so even if the Etsy shadow file gets leaked, let's say that somebody was able to get a copy of the Etsy shadow file off my server, that still doesn't mean that your password's been compromised. You should probably change it. It's probably a good idea. But it doesn't mean your password's been compromised, because they don't know what your password is. They can't, even if I made the Etsy shadow file world readable right now, assuming that you guys changed your password away from what it was originally, then nobody would be able to log into you. You understand? So even if I made that file world readable, assuming that you typed in, a reasonable password, nobody would be able to log in as you, even with your hashed password visible. And they, in fact, used to be visible on Unix systems. You used to be able to view everyone's hashed password, and in theory, this was secure. In practice, it was not, because what you could do is you could guess people's passwords, right? So I might guess for Bigints, his password's Bigints, and you do the hash, and you compare the results, and be like, oh, I got it, his password's Bigints, and now I can log in as him. And so we keep it hidden just to make that impossible, right? But even if I made Etsy Shadow world readable, that still would not help if you've changed your password away from the default. And so, yeah, you can pre-compute answers to a lot of them too, using what are called rainbow tables. But somebody earlier asked if I'd hacked before, and so on the old computer systems at UC San Diego, the Etsy password file was world readable, which I think it is even here, ls-l Etsy password. Yeah, it's world readable. Anyone can open up the Etsy password file. It doesn't have passwords in it anymore, so it shouldn't be called Etsy password, but there it is. And so you can see everyone's username. The password, though, is gone, but back in the day, it had the hashed password in there. And so we would have fun guessing passwords, cracking passwords, trying to guess people's passwords. And you'd be able to do it, too. Like, for every class, you'd be able to get the passwords of, I don't know, 3 or 4 people at least. And, yeah. So and then you would log in as them and mess with them and things like that. Like my friends were never malicious, you know, but like my favorite hack was logging in as I figured out my buddy Brian Dagenhart's password. Actually, I got that by sniffing his password. I ran an Ethernet sniffer, and so we were in the same computer lab together. He sent in his password over the interweb, not encrypted, and I captured it, and then I logged in as him. And he was on various, 3D graphics engines, mailing lists, and things like that. And so I answered emails from him. So like people were like, "Hey, how do you do an intersection between a line segment and a box?" I'm like, well, first of all, you have to understand the algebraic line equation, and then and so I wrote these like really long, detailed, thoughtful answers and signed it as Brian Dagenhart and sent it to the mailing list, and he started getting back all these emails like, "Wow, man, you're so helpful. Thank you so much. You're really good at this stuff." And because most people would be like, "Ha ha, I'm a moron," And I was just writing these really like multi-page, detailed answers, and he was getting all these like compliments. He's like, "What the hell is going on, man? Like all these people are like asking me for help now, and like what, like." It was great. Yeah. So Brian went on to rewrite Twitter, by the way. So they hired him to refactor the entire Twitter code base. So he's had an interesting life, from what I understand. When the teacher uses you as an example, yeah. So my friends and I, we would mess with each other all the time. But that's it for today. I don't like being malicious when I mess with people, but it was kind of funny if you think about it. Okay, so RSA Encryption will be due a week from today, and I'll put up the next zyBooks assignment as well. All right. So we'll see you guys on Tuesday. If you have any questions about RSA, you got the Help Center on here. And peace out. Have a good day.